on the Riemann surface.
Okay, so thank you for I want to thank the organizers for this invitation and the nice workshop. So I hope this talk will be of interest to you, even if we've seen lots of talks on discrete graphs, maps, and so they'll be kind of in the background of this talk, but this talk is on some project I've had with collaborators which are in here. So I mean, this program was initiated by François David, Antti Kupienen, and Rémi Rod and myself, and I mean the first question we had was, in some sense, do we understand physics? Okay, so it's Liouville quantum gravity is a celebrated theory in physics, and so they had correlation functions. They had Polyakov had introduced his functional path approach to quantum gravity, and and so what we wanted to do is really go deep into the physics literature and try to define directly out of it what is Liouville quantum gravity, at least for physicists, and the other way around, something that interests mathematicians is once you start with a path integral, say, and you construct a conformal field theory. So that was the first goal of our work, and the second goal is to go the other way around. Can you, from your conformal field theory, recover the action you started with? And so this is something that is often done in probability theory, and it's one of the big subfields of large deviations. Okay, so this talk will be about making sense of an action and trying to recover this action, and in particular, what happens in Liouville quantum gravity is that you know that it's supposed to be the quantum version of uniformization of surfaces, and what you get out when you try to recover this action from the conformal field theory is the so-called Liouville equation, and I'll discuss this point at the end if I have time. Okay, so first I'm going to give a short introduction and some motivations from the physics literature. Then I'll discuss Liouville quantum field theory on Riemann surfaces. So there'll be some overlap with the talk of Rémi Rod a few months ago here, because I mean, the audience, some of you were here a few months ago, some were not, so it's always complicated to choose how to do your talk, and so I'll do there'll be some new stuff, but there'll be some overlap. So first I'll discuss mainly in this talk, in fact, Liouville quantum field theory on the Riemann sphere. I'll discuss a bit Liouville quantum field theory on the unit disk, just roughly. Well, and before doing this, I'll just do a few reminders on Gaussian chaos theory. So, but I used to spend lots of time reminding this theory, but now I think it's a bit better known. So hopefully I'll go pretty fast here. And then at the end, I'll discuss what I was saying in the introduction, namely that I'll try to give a few ideas behind what is called the semi-classical limit of Liouville quantum field theory. Okay, and we'll see it has a relation with classical conformal metrics on the sphere with conical singularities. Okay, so so why study Liouville quantum field theory on the Riemann sphere? Well, first thing, and I guess maybe one of our initial motivations was it's an important conformal field theory which is indexed by a continuum set of central charges. Okay, so you know there are many ways to see the central charge. You can see it in SLE, for instance, when it's less or equal to 1. So it's a way you classify your conformal field theory and the correlations, so Liouville quantum field theory is in fact a conformal field theory given by with central charge 1 plus 6 q square, where q is given by gamma over 2 plus 2 over gamma for gamma less or equal to 2. So since q is going to appear often in my talk, I reminded it over there on the board. So in this talk, gamma will be between 0 and 2. Sometimes it will be equal to 2 on 1 or 2 slides. and Q will be given by this expression. So just to avoid confusions, there are two central charges when you do Liouville quantum gravity. There's the one that comes from Liouville field theory, which is what I gave here, which is greater or equal to 25. And there's a second central charge in when you do Liouville quantum gravity is on the planar map side, say, you know, when you put a statistical physics model described by a central charge less or equal to 1 on your planar map, you expect that at the end it converges to this conformal field theory, and in an independent background described by Liouville field theory, where gamma is equal to this. So this is an open problem in the field to derive this from maps. It's also called the KPZ relation. So there are two central charges. The central charge in Liouville quantum gravity, the one of the statistical physics model you look at, and the one of the Liouville field theory it's coupled to at the end, conjecturally if it's maps. Okay, so as I said, a second reason, and I think this has been emphasized a lot this week, a second reason to study Liouville quantum field theory is it's the conjecture scalar limit of random planar maps. So this was not our initial goal when we constructed this theory, but it kind of comes out free once you've defined these functional path integrals from the Polyakov's action. You get for free measures, and it's natural to conjecture the scaling limit of random planar maps. So two other things that are important. So mainly words, because for most of us, I imagine, because it's complicated theories, but there are links with important theories in 4D and in particular also in 3D, which is the so-called Weiss-Zumino-Witten model, which is which should have a relation, which is conjectured by physicists to have a relation with Liouville field theory. So essentially, it's ADS is anti-de Sitter space. It's they have theories of gravity with hyperbolic geometry models of gravity, and essentially when you project them on the border, you get 2D conformal field theories, and so Liouville is supposed to be coupled to an important theory of 3D gravity. Okay, so these are the references, important references we worked with a lot, and we still work with all day. Actually, it's I guess maybe some reference notes on Liouville field theory. There's this one, which is very important, one of the first by Nathan Seiberg, where in there's already lots of things. And then Nakayama in 2004, he did I guess it's the most recent huge summary of what we know on Liouville field theory, and it was written so after Seiberg's notes. So you see here that it's written Liouville field theory a decade after the revolution. So it was written after the revolution, and Seiberg's notes were written before the revolution. And the revolution he's talking about is the fact that this conformal field theory, though it's pretty complicated, physicists managed in 1994 and since then to compute exactly lots of correlation functions, lots of quantities associated to the theory. And so it was actually Seiberg in his notes said, well, what we need now is to compute exactly the quantities of the theory, and that was done a few years later, and so that was the so-called revolution. Okay, all right. So now let me speak about Liouville quantum field theory. So first, a few reminders. So what will be the kind of the backbone to construct the theory will be this Gaussian multiplicative chaos theory I was mentioning. So just a reminder. Now I think most of you know this very well. So Gaussian multiplicative chaos theory, it's about defining a measure of the form exponential gamma, a log correlated field. Okay, and that you integrate against, let's say, something absolutely continuous with respect to Lebesgue, but in fact Kahan's theory is much more general. You can integrate any Radon measure in his theory. So, but in particular, what we'll be interested in is integrating exponential gamma log correlated field against something which is absolutely continuous with respect to Lebesgue to start with. Okay, so that's the goal, and so I mean the strategy is pretty clear. That's what Kahan did, but then what was not clear I'm going to describe. That so he took a smooth martingale sequence of Gaussian fields converging to X, such that roughly the covariance here approaches the logarithmic covariance of my Wilds field X here. Okay, and so what he proved is within this martingale framework. So essentially, what he proved is okay. So you have a martingale and you converge almost surely to a measure. Okay, and this measure. So you have an almost sure convergence, and this measure is independent in law of the cutoff procedure you use to approach your log correlated field, and he called it a Gaussian multiplicative chaos associated to the covariance K of of your log correlated field, because of course this is ill-defined for y equals x. It's not a random function, so you can't take the exponential, so you have to smooth it and go to the limit. Okay, and so that was one of the first thing I did with Raoul in the field, was to show that, well, in fact, whatever log correlated field you take, in fact, if you take a reasonable cutoff, okay, so I'm not going to give the definition of a reasonable cutoff, but essentially any cutoff you think of, I don't know, a convolution, it converges in law to a measure which is independent of your cutoff procedure. There was so then this approach by Duplantier-Sheffield to in the case of the Gaussian free field, they constructed these measures as a limit of x epsilon, where x epsilon is a circle average of the Gaussian free field. And let me finish by so they showed an almost sure convergence along a cutoff which was not a martingale. And let me finish by saying that Shamov proved, in fact, that whatever log correlated field you take, if you apply a reasonable cutoff procedure, you converge in probability to a measure which almost surely does not depend on the cutoff. And actually, if it's a 3 or 4 line argument in here, you add it to this paper and you get this convergence in probability, essentially. Okay, so all this to say that, I mean, defining these measures is well understood today, and it's not very, and they're intrinsic. They do not depend on the way you approach them. So that's an important point, but it wasn't obvious like a few years ago when the field in the field. Okay, so what is important here for us is that that the measure you get at the end is different from 0 if and only if gamma square is smaller than 2d. So when you do, and this is going to be what happens in a few slides, we're going to work in dimension 2. We could also work in dimension 1, and so this result is relevant for these 2 dimensions, because when you have when you look at Liouville quantum gravity, it's a surface, so you can look at the frontier of the surface, and in which case you take d equal 1 here, and you need gamma smaller than square root of 2 for the measure to be non-trivial. And if you're working in dimension 2, you need gamma strictly smaller than 2. Since gamma square is smaller than 4, it's gamma smaller than 2 for the measure you get at the end to be non-trivial. Okay, and so there's this statement that says that it has a multifractal behavior, which can be described by this drawing, this simulation. So you see here, I like to show for the same log correlated field in dimension 1, I plotted the density of so I plotted this guy for epsilon small. Of course, you can, and you see that as gamma gets bigger and bigger, your measure, it concentrates more and more. So the blue one, gamma, is high, so it concentrates more and more on little sets, little fractal sets here that give huge mass. And when gamma is small, it nearly looks like the Lebesgue measure. Okay, it's absolutely continuous with respect to the Lebesgue measure, but for gamma small, the black curve is much more uniformly, the mass is much more uniformly distributed on the segment here. Okay, so now we have this theory to define measures. Okay, so now I switch to Liouville quantum field theory on the Riemann sphere. So, so the goal, you know, it's kind of like constructive field theory. The goal is you have a partition function which is described by exponential minus some Euler-Lagrange functional, and which you integrate against some background measure, some uniform background measure d phi, which does not make sense in mathematics, and so you integrate over all functions that go from R2. So the Riemann sphere, okay, I should add infinity here, but I'm going to say the Riemann sphere in this talk is R2, but I should rigorously add infinity here. So of course the Riemann sphere is R2 union infinity by the stereographic projection. And so the goal is to define this thing here where the action is given by this term here, these three terms. So you have a gradient term, and we know pretty well how to take care of this gradient term since it's the action of the Gaussian free field. So here you have some q, which I already introduced, times the curvature of the background metric. So this is some background metric on the Riemann sphere. Okay, it's a metric tensor, plus this exponential interaction term. So this says that Liouville field theory is an interacting field theory. Okay, so you want to make sense of this, so essentially, well, since we're going to get a conformal field theory, we can define. We were able to define it for all g's here, but and they're related to taking g equal g hat by some transformation. So in the sequel, by the so-called Veil anomaly. So we're going, but so just to simplify things, I'm just going to work in this talk with g hat, and essentially what a conformal field theory says is that nothing's going to depend on the background metric I put. So I can choose the metric tensor of the sphere, which is given by this expression. So I recalled it on this left board over there. Okay, so in fact, this you cannot define, and you see this in the physics literature. But there is one thing that seemingly you can define when you read Polyakov, Seiberg, and all that is the following thing is rather, so depends on the viewpoint, this correlation function for n greater or equal to 3. This they seem to define, but this no. So this brings us to the following definition. So we're going to try to define these quantities here, which are correlation functions, or if you put a functional in here, you can add a functional here. It's going to be a probability measure or a measure on phi. Okay, so before going to the definition, our definition of this partition function or correlation function, I'm going to make a few reminders. So I'm taking the sphere background metric, right? And so for all C and R, we'll see where C appears in a few minutes. So I reminded most of this stuff on the board on the left. I'm going to introduce the green function with vanishing mean on the sphere, and I'm going to introduce the so-called Liouville field, which is going to be my Gaussian free field plus this metric tensor, the log of the metric tensor, plus C. And so I'm going to introduce these vertex operators, which will correspond to this. Okay, so this is going to, the vertex operator are going to correspond to these exponential phis. I'm going to regularize my free field. So you take, for instance, people here like to take the sphere, the circle average. And okay, so these are going to be my conventions. So I'm going to introduce the free field in a regularized version. And okay, so when you start trying to, when you start trying to make sense of this stuff here, well, what you know is that roughly this is going to be a free field. Since you're adding a curvature, you're shifting your free field by log of g hat. Since the curvature in Riemannian geometry is minus Laplacian log of g hat, so if g equals g hat. So essentially, what you want to do to define this stuff is consider a Gaussian free field and just shift it by this quantity here. Now if you do that, it doesn't work. It's not going to be conformally invariant, so you start trying different stuff and everything, and you realize that if it's not conformally invariant for the following reason, if you start trying to make sense of this action with just a free field plus a shifted plus this shift here, it's essentially because when you take a free field and you apply on the Riemann sphere and you apply a Möbius transform, you're not equal in law to the free field in the beginning, right? Because this has vanishing mean in the sphere, and this does not, or not necessarily. It's not true for all Möbius. So essentially, what you need is to average out the average value of your Gaussian free field. So there's only one way to do that. It's to use the Lebesgue measure. If you want something to be independent of a general level, well, you need to integrate out the general level with respect to the Lebesgue measure. And so this is what leads to this kind of to this definition. So as I told you, I'm taking exponential alpha phi here. So it's going to be C plus my shifted Gaussian free field. And the C here is going to be integrated with respect to Lebesgue. Okay? dc. Now, here this term is 0, so and this term here is the curvature term I was talking about. And so the curvature of the sphere is 2, right? So at the end, and so if you take a functional, this is how you want to define your generalized correlation function, as this limit here, okay? Now, what saves the day essentially is that, okay, you integrate with respect to Lebesgue, but you get a finite quantity, because here you have this cosmological constant, exponential minus mu, this total mass here. And so even if you're integrating with respect to Lebesgue, which has infinite volume, you get at the end a nice clean finite measure because of this exponential minus term here. See, you're integrating exponential gamma c with respect to Lebesgue. And so, in fact, it's not that difficult then to compute this quantity, because essentially these guys you can put them in here by using the Gersonov transform. You know, when you have exponential Gaussian, it's equal in law to I mean, this Gaussian here, if you multiply by this density, it's like shifting it with the green function applied to these points. So you can get rid of this quantity in the limit in the sense that you can put it in here, and at the end you can get a pretty. So here I'm reminding the definition, and of course when you compute this, you can introduce a probability measure by taking this ratio here. So you put a functional and you put it equal to 1, and it makes a ratio, and you get a nice probability measure. And so, as I said, to make these guys converge, you use Gersonov, and at the end you can really write an explicit formula. And so at the end you get that your correlation function for f equals 1, so here I'm writing it for f equal 1. At the end you get these global terms here in front, but especially you get times a gamma function. So here's the gamma function. I think everyone knows it, but I'm reminding it. So sum over alpha I minus 2q, mu positive, and you get this inverse power of a Gaussian multiplicative chaos here in the sphere background metric, and you get these logarithmic insertions. Okay, so, and what you see is, of course, the gamma, so what you realize is that this guy is, you work a little bit, but you can show that this guy is not infinity if and only if alpha I is strictly smaller than q. And of course, you see that this gamma function exists if and only if sum of alpha I is strictly greater than 2q. And so you see that you recover what physicists tell you, namely that if you want to define properly your correlation function, you need at least 3 points, n greater or equal to 3, since you can't have alpha I smaller than q and the sum bigger than 2q unless you have 3 points. Okay? And if I have time at the end, we'll see it's some topological constraint, in fact, of the sphere that explains this. Okay, so you can define it properly, and then you want to recover really what you see, what you read in physics, that they have these so-called conformal weights. So yes, this Liouville field theory on the sphere is joint work with François David, Antti-Kupiainen, and Rémi Rod. So François and Rémi are actually here, and so I'll abbreviate them by DKRV in the sequel. And what you see is you get the conformal invariance I was talking about, namely that if you change your points xi by some Möbius transform here, and you shift your free field, your Liouville field by this term here, so the coordinate rule of what is called the change of coordinate rule of Liouville field theory, then you get the same thing up to these conformal weights which come out. Okay, and so to prove this, essentially, you play around with Gersanov and you use this property I was talking about, is that since your Liouville field, you're shifting it with Lebesgue, you don't see the average level of the field, and so then you use the identity that if you take a Gaussian free field, you compose it with a Möbius and you take out its mean, then you get the same Gaussian free field in distribution. So you can define these correlation functions, and so you can define also the so-called Liouville measure. So what is the Liouville measure? Well, so I define correlation functions, but I told you I can define more. You can plug in some function of the free field, of the Liouville field, and you get a probability measure. And so if you try to take exponential of the Liouville field under this probability measure, well, you get this thing here. So I kept it on the board so we don't forget. You get this Gaussian chaos with exponential of logarithmic singularities, and so you divide it by total mass, and what you see is you get a reweighting of your probability space by this some inverse power of the total mass of your Gaussian chaos. Okay, and you get this this independent gamma distributed random variable, which is the total mass. Okay, and just for those, I explained it in more detail in other talks. So, but essentially, I like talking about. So this is really what comes out of the action, and this gamma law is important because, in some sense, it enables you to identify very quickly from planar maps what measure should be the limit of planar maps. And so this is what I explain here, maybe a bit briefly. But so as I said, your Liouville measure has total mass a gamma distributed variable with these parameters. And so imagine you take all the alpha i's equals to gamma and n equals 3. So in this case, well, you get, so there was a talk by Omer Angel about the fact that you can equip your a triangulation with a conformal structure. So you equip it with your conformal structure, you map it to the sphere, and you choose 3 points where you're going to map. What you do is you take your planar map and you take 3 points uniformly on it, for instance, and you map it to 3 fixed points on the sphere. And what you get, okay, is this is a circle packing, which since our circle packings all over the conference, I had to add one too. So I asked François to make one. So if you circle pack or say your sphere, or you conformally map your triangulation into the sphere, and you put a little mass in each triangle, at the limit you expect to converge to these measures I'm describing. And so there are 2 ways to do. You can either take your map and condition it to have volume 1, but you can also use Boltzmann weights to pick your map. And in that case, you can identify which gamma is going to be the limit of your map with the asymptotics of the map. Okay, so essentially for the uniform one, if you take the set of triangulations with 3 marked faces, okay, then we know since Todt that it has some the number of such triangulations is given by this formula, and this factor is important because if you throw a Boltzmann weight, if you pick it according to a Boltzmann weight and you renormalize properly, at the end you're going to get a random variable for the total mass, which is distributed like this guy here, with parameter given by this. So if you take all the alpha i's equal gamma and you solve your equation, you see that gamma is worth square root of 8/3. So I mean it matches. Okay, so this is one simple way to identify the gamma, which is going to be the limit. So you can, okay, so this measure exists if you have these two Seiberg conditions, as I told you. So you have these conditions on the alpha i's and the x i's you use to define your map. So if you're lost, you can always look at this formula. So, but you can also condition it to have volume 1, and in that case you get rid of the gamma distribution, and so this is going to be the limit of planar maps conditioned to have volume 1. Conjecturally, it's going to be the limit of these maps, and in that case you get a more extended, you get a more relaxed condition to a more it's less restrictive, and you can show that these unit volume measures exist if and only if you have this inequality. And in particular, you see that once again you need 3 insertion points, okay? Because if this q minus sum over your insertion weights over 2 is less than this minimum, of course the sum over 2 is strictly less than each of these guys. So you need at least 3 alpha i's for this to work. So once again you need 3 insertion points. But I'm going to come to this in a minute. Nonetheless, you can make the following observation, that if you want to have only 2 insertion points, the only way you can, I mean, you can want to put alpha 1, alpha 2, and the third one equal to epsilon and go to the limit, for instance. Okay. What you see, if you want to do this, you have to take alpha 1 equals alpha 2, and then you're allowed to take a unit volume Liouville measure with weight alpha x1, some point you've chosen, alpha 2 x2, and epsilon x3. Okay, and well, so I had a movie actually on my circle packing. I don't know if I have time. There's a movie on this. I have to show it. It took François some time, so you see my circle packing. So you see, this is what a circle pack triangulation looks like, and so okay, so let me talk of this 2 point. So there's also been as you know, really developed in a big paper by Duplantier, Miller, and Sheffield, the 2-point approach. You know, these so-called 2-point quantum spheres. And so what's interesting is there's a work in progress here by these 3 people. So 2 of them are actually in the room, Aru and Sun, which is about relating these 2-point approaches to these the approach we developed with where we see we need 3 or 4 or 5 points, and I guess it's here's a reasonable. So the difference is the following: we work with random measures, right? And so in this 2-point approach, they work in equivalence classes of random measures. So what does that mean? So they call it equivalence classes of quantum surfaces. So they have measures on let's say the sphere with 2 points, 2 marked points, and if you apply a conformal map which fixes these 2 points, you can identify. So you can identify the two volume measures you're working with. Essentially, you're in an equivalence class. So, for instance, if you take 0 and infinity, okay, roughly you identify measures which are related by a scaling relation. Okay, and so I guess it's a reasonable conjecture that so you're allowed to scale your measure as you want, and so I think well, it's reasonable to assume, and I think most people working on this agree, is that if you take our three-point approach and you make one of these, so you see you have a point, you fix it, and you make its weight go to 0. Okay, see, it disappears from the definition of the measure. And if you rescale properly your our unit volume Liouville measure by some random factor here, so I'm working in this equivalence class so I can scale, well, you'll converge to the 2-point unit area quantum sphere. Okay, so this is so people can relate. And so what happens also is, since you're rescaling, so you're going to go to 0 or infinity. I mean, it's a symmetric problem, but so if this guy goes to 0, the metric tensor of the sphere should disappear because you don't see it anymore. And so that's why, for instance, in their approach, there's no metric tensor of the sphere. Okay. All right. So let me shift. So I guess so. Here was a description of Liouville quantum field theory on the Riemann sphere, and let me shift to the unit disk. So you can do the same game. Okay, in the disk. I mean, the action is going to be, this guy here inside, and you're going to have also these boundary terms where okay, so this is the Ricci scalar curvature inside. So if you go with the flat metric, this is 0. Okay, and you can take the and so on the border of a disk, you on the frontier, you have also a Ricci scalar. Well, it's called the geodesic scalar curvature, and it's worth 1. So here it's important, and you can also reweight by these exponential, and so you get what is called Liouville quantum field theory on the unit disk. And essentially, you can go through the same kind of constructions, and then define the same kind of objects. So the main difference is that the Gaussian measure, the Gaussian chaos measure you're going to work with to define the object is not going to be this one, the one from the sphere, but it's going to be this one. So I really stress when I'm working with the disk. I'm just going to work a few slides with the disk, and then we'll shift back to the sphere. Forget about the disk, but I just wanted to describe this framework too. So you have insertion points xi with weights alpha I, and well, the measure you're going to work with is going to be this guy here. So you get a Gaussian chaos, but you're integrating, so these log singularities, and especially you're integrating something that really diverges. The expectation of this guy is infinity as soon as gamma is greater or equal to square root of 2, and so what you have to do first is show that this random measure is indeed finite, and it is if and only if you have these so-called Seiberg bounds. But I insist on the fact that it's not exactly a Gaussian chaos, because you're integrating with respect to something that is not L1. Okay. This function is not L1 as soon as gamma is bigger than square root of 2. And this is one of the things I like a lot about these Gaussian chaos measures, is that they enable you to integrate things that are in fact not Hadron measures. And so I think maybe a nice conceptual exercise or project would be to extend the theory and see how far you can go in defining the exponential of free field, say, against something that is not a Hadron measure. And these are examples of this, that they appear in Liouville field theory. Okay, so, well, I'm not explaining exactly where this measure comes from, but you get a different measure which you have to show is finite. And essentially, well, you redo the same stuff, these functional integrals that you integrate with respect to Lebesgue, the level of the field, and at the end what you get is the same kind of random measures in theory, where you replace, well, our Gaussian chaos on the sphere by this measure I just described to you. In the formulas you get, of course, you see curvature, so you're going to get you're going to get random measures of this form, where essentially here instead of 2q you get q, because this is you see the curvature, okay, and you can also add a boundary measure, so it's a bit more complicated to write down, but at the end you can work out and show conformal invariance of these systems and make conjectures on maps that you embed in the disk in a conformal way. Okay, and you can also, we also pushed it to the torus with François David and Rémi Rod, and in this case they're a bit, it's a bit different because the conformal class of a torus is, they're not, you can't conformally map any torus to another one, so you have to integrate out some on moduli space, and so in that case there are some extra pieces you have to put in the theory, but you can still manage to write something which has the right conformal invariance, and of course in that case, well, q disappears because curvature of torus is 0. All right, so so now this was a very quick and maybe a description of a kind of objects we can construct, and so just to summarize, remember that, so here's the disk, but I'm going to work with the sphere, but you have an action, and you show you can define random measures, random correlation functions from them, and well, you can also try to in some sense recover the action from your theory. So this is what is called the semi-classical limits. It's when you have like Schrödinger operator and you make the Planck constant go to 0. If you represent it with the Feynman-Keck formula, you see that you're doing large deviations, and in particular, if we recover this action, well, the minimizer we want to recover also the minimizer, and it's going to be described by the Liouville equation, which is why it's called Liouville quantum gravity, and these equations are linked to the classical uniformization of surfaces. So let me describe it's ongoing work with Rémi Rod and Hubert Lacroix. So let me first remind what are classical conformal metrics on the sphere with conical singularities. So so the main problem is that you want, so I mean, by the Gauss-Bonnet theorem that on the sphere the curvature is 2. The average curvature is 2. Okay, but you can want to put another curvature on the sphere. In Liouville field theory, people often say, oh, it's a theory of negative curvature. Okay, so you can't put negative curvature. Negative constant curvature on the sphere. That's impossible by Gauss-Bonnet, but a theory that has been developing the past few years in calculus of variations or geometrical PDEs is the following problem: is to construct a conformal metric on the sphere with conical singularities. So you're looking. So you take points on your Riemann sphere x1, xk, and you want to construct a surface where outside these points you have a constant curvature k, and where, well, around these points you have a logarithmic singularity. So this is the problem that people in classical geometry have been tackling for the past 10 or 15 years. So because, well, it has many links to other physics theories. So here are two, for instance. And so what you want to do is solve the Liouville equation here. So outside these singularity points, and you want your function to have logarithmic singularities. Okay, so this, and now if you solve this prescribed curvature. So in the rest of this talk, k, okay, the curvature I'm going to suppose constant. So if you want to solve this equation, well, you see that you have to introduce the Euler characteristic, which is 2 for the sphere, but in this case you see that the Gauss-Bonnet formula will give you something else. Okay, the curvature of your surface, you can you can, for instance, if you take these guys positive, you can make it, well, even become negative and construct hyperbolic surfaces on the sphere. If you put enough insertion weights here. Okay, so by the Gauss formula you get this, so you're happy. This means that your curvature, you can really diminish it. Okay, so an equivalent formulation of this is, well, so you want to solve this curvature problem. So this is the Laplacian on the sphere. You want to solve this thing, so you write h as some part which has the logarithmic singularities plus the smooth part. Now, if you do that, so you take out the log singularities of your what you're looking for, you end up with trying to solve this equation up here. So minus Laplacian of this smooth function is equal to the Euler characteristic of your surface, so times this. And at the end, the metric you'll get is this smooth part and the logarithmic part. Okay. Now the theorem is the following by Troyanov, and it says that it has a solution if and only if you have this condition here. So if and only if 2 minus 1 over 2. No, it's not an only if. Sorry, it's an if. Okay, it's an if. But okay, for the only if. But let's say, okay, to start, if you have this condition, okay, you can solve this equation, and so you can construct a conformal metric with conical singularities and with curvature given by this term here. Okay, so 2 minus 1. Now you see, so how do they this is what we call the Moser-Trödinger condition. I mean, okay, and why is this? Because essentially, if you want to solve this equation here, okay, this curvature equation, you need to, well, it's calculus of variations. You need to minimize the associated action, the Euler-Lagrange action of your problem, which is given by this guy here. Okay, so you take your gradient in the sphere, and you take out this the curvature and this logarithmic term minus its average. So if you minimize this guy, it's not very hard to see that it's going to be the solution of your curvature problem on your sphere with conical singularities. And so, okay, if you want this to have a minimum, you need this guy here, okay, to be controlled by the gradient term. So the Moser-Trödinger condition or inequality, it's an important inequality in analysis because it's a Sobolev embedding theorem essentially. And so you see this inequality. Well, if you multiply by the same term, okay, so this is the so-called Moser-Trödinger inequality when there's singularities. If you multiply it by this fixed term, I'm doing nothing, you see that the gradient term will control the logarithmic term. Your action has a minimum. It's bounded, or at least it's bounded by below, if you get this. So this Sobolev embedding theorem, which tells you that the gradient controls the exponential of an h1 function, okay, the constant in front is really very important. And you see that it tells you that this guy has to be smaller than 1. And so you get this natural condition that if you have this, okay, so if you can control by the gradient term an exponential term, okay, the Sobolev in the Sobolev embedding theorem, you can solve you can give a minimum to this action, and you can solve a curvature problem. All right, and so this is what I said. It's a classical Moser-Trödinger condition, and so why did I call this the quantum Moser-Trödinger condition for the Liouville measure? Well, the unit volume measure, it exists if and only if you have this. Okay, so it's very, very close to this condition. It's really the quantum version of this Sobolev embedding theorem. And so what's going to be the semi-classical limit in this context? Well, you're going to take your insertions alpha I to be chi I over gamma with chi fixed, and you make gamma go to 0. So when gamma goes to 0, you're looking at the semi-classical limit. It's like the Planck constant going to 0, and you see that you recover exactly the Moser-Schrödinger equation. So they're compatible. So the kind of things that we can prove are the following. So recall that I have my unit volume Liouville measure in the sphere, or I can look at the unit volume Liouville field, so which is going to be the free field plus these terms here under this probability measure. And what we can prove in this context is that, well, if right now we're still a bit stuck here, but if we have this condition on my Euler characteristic in this regime here, well, the Liouville field as gamma goes to 0, gamma times the Liouville field minus the non-regular part, it converges in probability to the solution, to the unique solution of these curvature equations. And in fact, our techniques enable us to state also a central limit theorem that we can control the fluctuations, and they're given by a massive Gaussian free fields in this modified background metric and all this. So, okay, maybe it was a bit fast, but essentially what we did is we showed how, so we took an action, to summarize, we took an action, the Liouville field action. We constructed a conformal field theory, measures the Liouville field and everything, and then the other way around. So in the semi-classical, we showed that in the semi-classical approximation, we showed that we could recover the minimizer of this action. Okay, because this is the minimizer of the Liouville action, and so well. Of course, what we want to do now is not just recover the minimum of the action we started with, but we also want to recover, of course, the action itself by large deviation theory. And in fact, we can, in some situations, we can go further. We can even give precise asymptotics on the partition function of our system in this semi-classical approximation. And so, one issue here, for instance, is if you know, physicists have exact formulas for the partition function. That's why it's popular in the physics community, this Liouville field theory, because they can compute things. And for instance, you can check the validity of these formulas in the semi-classical approximation. And this is how actually physicists use this semi-classical approximation and so on. Okay, so as I said, well, we only derived it under certain Moser-Schrödinger conditions, but well, we're working on this, and we're working on exact asymptotics of the partition function within this regime. Okay, well, I think I'm done. Thank you.
If you can do the torus, is there any more difficulty doing any topology?
Well, the thing is, yes, because in the case of the torus, you have a okay. In any topology, we can define if you condition on knowing what the moduli is, then we know how to describe the measure. But then you have to integrate on moduli space, and then you need theories from classical geometry, extensions of Bell-Petersen metrics, and in this case, I'm not sure if it's been done in the community of
choosing which measure you will integrate over the moduli space? Or?
Yeah, you have expressions in the case of the torus. In geometry you can compute this thing. It's been done by physicists, but it can be made rigorous. But you get a nice expression. In higher genius, it seems there are no expressions. I've discussed this. No expressions, and so for the existence, I don't know if there what has been done exactly.
For the cycle now,
Yeah.
do you have any explanation in terms of? Okay, can you relate that? Is it possible to understand this in terms of the points of the field that may not exist for some variable singularity?
Well, it's not even, no, I mean, it's orthogonal to the thick point issue, because the thick points are special points of the field. When you fix your point, okay, let me go back to okay. When you want to integrate this stuff here, okay, this is the log of 1 over x minus xi. And so xi is fixed. It's a fixed point. So essentially, when you look at the free field at size, regular line at size epsilon, it's worth square root of log 1 over epsilon. Because the point is fixed. So it's just a Brownian motion around this point. And so since it's just a Brownian motion around the point, well, you see that you get minus gamma square over 2 log 1 over epsilon. You have a really flattened measure. That's why you can integrate more nasty singularities. But of course, it's because this is a Brownian motion around xi, because xi is fixed. If you took it random, then it would be an issue of thick points behind all this. But here you can forget about thick points. Around this, there's nothing happening special with respect to the free field.
Other questions? Yes.
Say, at the beginning, you mentioned on the first slide, well, can you show that again, the beginning, all these,
This?
yes, all these connections to
Ah.
supersymmetric gauge theories, ADS, CFT. If you want to extend what you're doing into one of these other areas, what do you think is the next interesting place for mathematicians to try to go?
Well, I guess maybe if I have time, I'll try to learn what is anti-de Sitter space. You know, this Lorentzian hyperbolic geometry, but I'm in 3D, but I'm not a specialist of that stuff. So this, I think, is going to be okay. Let's say I think this is going to be understandable, but this I'm not sure.
Yeah, actually, I think the third line is very active at the moment. But of course, the physicists don't play with the rules, by the rules, as you know.
And there are other types of mathematicians working and proving things on AGT.
There are many mathematicians.
I think Okunkov is working on this with Nekrasov and all that.
But also French one.
Yeah.
Eric Vassereau.
There was a whole semester in Montreal in this summer on this subject. The SCFT correspondence.
Yeah, this is very active too. I'd say this, okay, but this is because it seems more understandable to Lorentzian 3D hyperbolic geometry.
Other questions? No, if not, we thank you.